What is the message written in these dark vertical lines?
All right, hey everybody, welcome to one more week of physics. We only have a few left. I think we're down to 5.5 weeks. Crazy to think about. So, kind of sad, but exciting that we can maybe get past all this. But at the same time, I'm gonna miss all of you. I can't believe I may not actually ever see you guys again till next year. Whatever. Crazy. Let's not talk about that. Today, 3 things. Really cool kind of application of everything we've been learning today. If you didn't get the announcement, test Thursday. Another one of those Google form online tests. It'll be 10B because this is all the stuff on color and stuff like that. But today's the last lesson. Tomorrow review day. Wednesday review day. Test Thursday. So today, star stuff. 3 things that we're going to talk about today. One is, what are stars made of? And all of this is going to use this light. We're going to use the light because, well, that's all we can get from stars, right? Is the electromagnetic waves that they send us. That's all we have from stars. Other than the sun, we get some particles and stuff like that from the sun. But other stars, all we have are their light. So, what are they made of? Well, light tells us. How old is that star? Well, we use what it's made of and the light from it to figure out how old it is. So we'll talk about that. And number 4, are you kidding? Well, here we go. Mr. Ager cannot number. 1, 2, 4. Just, here too. Not just my worksheets. And so number 4, which should be 3, which way is the star moving? So is it going towards us? Is it going away from us? Is it standing still? And how do we know? Again, it all comes back to the light of stars. Check out the next couple videos. Me, bouncing back in between me, some notes. Neil deGrasse Tyson, some other guy I don't know. Me again. And then me again. So, see you guys out there.
The secret message, those black vertical lines in Fraunhofer spectrum? What makes them? They occur when the light waves of those particular colors are being absorbed. It happens on another level of reality, far smaller than the world we're used to operating in. The sun's surface radiates light waves of all colors. If you look at sunlight through a prism, you'll see its spectrum. When you magnify the spectrum with a telescope, as Joseph Fraunhofer did, you raise the curtain on the electron dance within the atom. When the energy of the electron flags and it drops to a lower orbital, the light wave it emits scatters. Most of it doesn't reach us. That leaves a dark gap or black vertical line in the spectrum. These dark lines are the shadows cast by hydrogen atoms in the atmosphere of the sun. Sodium atoms cast different shadows. Their electrons dance to a different tune. A grain of table salt is composed of sodium and chlorine atoms. 10 million billion of them doing their crazy dances in a single grain of salt. And a single iron atom with 26 electrons is like a great big production number in a Broadway musical. When you look at a star with a spectroscope, you see the dark lines from all the elements in its atmosphere. Show me the spectrum of anything, whether here on Earth or from a distant star, and I'll tell you what it's made of.
All right, so everybody, so how does Neil deGrasse Tyson know what stars are made of by looking at their light? Well, 2 things. 1, looking at the spectrum lines from the light. So we're actually looking at those black lines that the light is missing. So it should be a continuous spectrum, but it's not. There's black lines. Now, there's a little bit of confusion. Actually, let me jump over to that picture of the sun. So there's the sun's light going from violet all the way to red, including the very dark red. And it's not a continuous spectrum. It's not violet to blue to cyan to green to yellow. I mean, it is, but then there's very distinct black lines. This is called absorption lines. So these lines are the light that has been scattered out of the spectrum due to the atoms that do their transition at these energy levels. All right, so this is called absorption lines, because it looks like it's absorbed each of these lines. It's really scattered them out. Emission lines is the reverse. Emission lines would be completely black across, nothing, with a very distinct line at each spot, where there's a black line on this, where the element sends out the photon. And so it's just a very small, it's the exact same concept, even though they look completely different. One, absorption lines we get by looking directly at the light source. So if we look directly at the source of the light, the star, because that's what makes light in space, is a star. When we look directly at the star, the light we get shows absorption lines. However, if we look at reflected light in space, like planets or nebula or any kind of dust or comets or anything we look at space, anything besides stars, then we see emission lines, and we can see very distinct emission lines from those things. So it's kind of this differentiating between the why is one black and then all of a sudden we have full color, but it's the same idea. So anyway, the second bullet there, if we jump back at it, is that the light will show us all the lines at once, and we have to decode that picture. So if we look across this spectrum, we just see a ton of different black lines. We don't see individual elements. It doesn't say here's hydrogen, here's lithium. You have to know what this given spectral lines for that element look like, and then you look for them, you hunt them. And that's what we're going to do in this example here. So I've got an example of giving you the spectral lines for lithium, hydrogen, helium, and sodium. All right. Each one's got very distinct dark lines amongst those things. And then finally we have an unknown mixture. We can call this the star. This would be like having the star here. So what elements make up this star? Well, I've already done the work here, but you've got hydrogen and helium. Well, how the heck did I know that? Well, I looked at the lines. I actually started with each of the elements. I said, okay, lithium. Is there any lithium in this star? Well, if you look at this first line, that one might be lithium line. I don't know. Let's look at the next line. The next line going over, kind of in the middle, so I'm working from left to right here. The next line, I see, okay, here's about here. I come down and I see, nope, there's no 530 nanometers, not exactly 530, but I look down, there's no line in this unknown substance corresponding to this lithium line. So I can pretty much say there's no lithium in this star. It's not giving me the absorption lines that a lithium atom would give me. All right, look down at hydrogen. So I see the first line of hydrogen on the left here. Sure enough, boom, I see that one. All right, let's verify. Look at the next line in hydrogen. Yep, I've got a line there. Finally, last two lines in hydrogen, I see both of those in the unknown. So I can safely say that the unknown has all of the hydrogen lines, and so hydrogen is in the unknown substance. All right, helium, yes, first one, yes to the second one. The third one's interesting. It looks like it lines up with the sodium, so I can't really say that one's there. That might be from the sodium. But then the other three are also in the unknown if we come straight down. And so I can safely say that there is helium. All the helium lines show up in the unknown. So what about sodium there? Well, sodium's only giving me 2 lines for sodium. The first of the sodium lines is not showing up in the unknown. The next one is, but it's because it's the exact same line as helium. So that line we see in the unknown is not coming from sodium, it's coming from the helium. And we know that because the other sodium line is not in the unknown. So what elements make it up? Helium and hydrogen.
Like all stars, it's basically a giant nuclear reactor. The fusion reactor inside a star burns hydrogen, the simplest, most common element. The reaction fuses hydrogen atoms together, producing helium and energy. And when the hydrogen runs out, stars keep burning by fusing helium into carbon, then carbon into oxygen. When small stars like our sun make carbon, they begin to die. Now, gravity begins to crush the center of the star. The star's outer layers are pushed outwards. They expand into a huge ball of gas called a red giant. While the outer layers expand, in the center of the sun, gravity will have the opposite effect. It'll crush the sun's core to just a millionth of its original size, about the size of the Earth. Now, it's a dense ball of oxygen and carbon called white dwarf. In our solar system, this will be the end of the story. The gas from the dying star will gradually disperse, but the tiny white dwarf will burn for billions of years. As the white dwarf sucks more and more fuel out of its companion star, it gets heavier and denser and less stable. Inside, carbon and oxygen atoms are about to fuse together, and that's bad news. The moment the white dwarf star starts to fuse carbon and oxygen into iron, it's doomed. Suddenly, the white dwarf explodes.
All right. Hopefully you enjoyed that quick little snippet about supernovas, kind of the life of stars and what happens in them. It's a way longer movie, about 40-minute thing on supernovas. We're not going to work through that whole thing, but hopefully it's kind of cool. But big takeaway from that is that throughout the life of a star, it builds bigger and bigger elements. So when a star first starts, age, so we'll start with age, and it increases age. When it first starts, it's just taking hydrogen and turning it into helium. It's making very light elements. But as it gets older and older and older, the helium starts fusing together to make beryllium and carbon and bigger things. And then the carbon can start to fuse together as it gets older and older. And eventually, if it's not big enough, it just makes its carbon and oxygen. They can't really fuse it. It doesn't get enough energy to fuse these together to make anything bigger, and it just kind of stays there and dies out. It just kind of fuzzles out because it just doesn't have enough energy to continue. So once it burns up all its other stuff, it just kind of goes away. However, if it does have enough mass and enough nuclear fuel to fuse together these bigger elements, then eventually it will make iron. When it makes iron, it can still fuse iron together with other things, but you actually don't get energy released with anything bigger than iron. It actually takes energy to fuse together things that are bigger than iron. So if I want to fuse together iron to make bigger elements, which is where all the elements come from, I lose energy. So I need a very big blast furnace all at once to make those. And so we call anything bigger than iron a supernova element. Any element bigger than iron was made in a supernova in this universe somewhere. All other elements in the universe come from normal star operation, but anything bigger than iron came about in a supernova. So big idea, smaller, lighter elements, not smaller, but the lighter elements are in young stars, and the more heavier elements you see, the older we know the star is. So hopefully using that can help you answer the questions on the homework about age of star. All right, hopefully that ambulance, or as a fire truck. Hopefully that fire truck brought back the idea of the Doppler effect. The Doppler effect is that change in frequency of a wave due to the relative motion of the object and the observer. So, quick review. If an object is coming towards you, then the waves that it's making get squished together, which is a higher frequency, shorter wavelength. All right? If that object is moving away from you, then it produces a lower frequency. So we saw lower frequency and a longer wavelength because it has stretched out those wavelengths. All right, so red shift and blue shift is something that happens with light. It's just a Doppler shift with light. Doppler is not just sound, it's not just water, it happens with light as well. Red, it shifts towards the red end of the spectrum. Or sorry, red is a lower frequency than blue light. So we call it red shifting if it's getting lower, and we call it blue shifting if it's getting higher in frequency. Finally, the line shift. The spectral lines that make up the element, or in the element that make up the light, actually shift where they show up. They don't show up at that red 656 nanometer red for hydrogen. It shifts one way or the other if that object is moving. And so what would that look like? All right, so I've got the spectrum for hydrogen here. Quick refresher of that. It's made up of a violet light. You can look at the old homework too. Yes, or last homework, I've got this same spectrum there. So violet light at 410 nanometers. It's made up of blue violet light at 434 nanometers, blue green 486 nanometers, and then red down at 656. All right. If this object was moving away from us, okay, so it's moving away. It's stretching out its wavelength. It's making longer wavelengths. So this violet that's 410 would shift towards the red end of the spectrum. It wouldn't show up at 410. It would be stretched out a little bit. And it would actually look like a different color. It wouldn't be violet. It might be blue violet. So instead of having a line here where it is, it'd be shifted to the right a little bit. And so I'll have a little line shifted a little bit. All right. Got a blue violet line here. It's going to shift as well. So the next line over will shift. But it won't be blue violet anymore because it shifts. It actually changes its color. Just like the fire engine changed its sound when it went past us, the light actually changes its color as well due to the thing. So this blue violet now is no longer blue violet. It's just straight blue. Oh, it'd be just straight blue. All right. And then the blue-green line, it shifts as well. But it's also going to change color, and it might change to green. Instead of being blue-green, it's actually now green. All right, so all these lines, they stay exactly the same far apart, same distance apart, but they've shifted to the right a little bit. And then finally, the red light here that's very close, it will shift as well. And rather than being that nice bright red at 656, it's actually going to shift as well, and it's going to show up as a darker, much lower energy red. So these normal hydrogen spectrum will show up shifted towards the red end of the spectrum if it's moving away. If it's moving towards us, well, all of these lines would just be shifted the other direction. All right.